Okay, so today I am going to go over the concept of an adiabatic flame temperature of a steady state system. First, I'm just going to draw a model, and then we're going to apply what we know about adiabatic and steady state systems to create our equations, and then we're going to use an equation called ChemCAD 107, and we're going to put it into our Python in order to solve for the final temperature of this system. So let's say we just have this system here, and we have something going in. This is going to be our fuel. And for this example, we're going to use methane, ethane, and propane. And then we are also going to have air going in here. And it's important to note that this is air, not pure oxygen, because later we're also going to have oxygen and nitrogen going in. For our equations, it's not pure oxygen, we're going to use air. We also will have an initial temperature, and for this system, it's going to be 298 Kelvin. Okay? So then we are going to have, this is what's going in, out. We're just going to have our flame. So this would be like if we had just had like a lighter, you have your fuel going in at a certain temperature, but the temperature going out is this flame, and so it's going to be a substantially hotter temperature. So we'll take note of that when we do our energy balance equation. And so flame we can also just call a hot gas, because that's essentially what it is. And so we are going to use that for what is coming out. Right now we're just going to, since we're solving for our final temperature, we're just going to write high temp. It's going to be definitely greater than 298 Kelvin. So the next important thing to note in this setup is that it is adiabatic, which means no heat transfer. We also want to note that it is steady state, which means that the change in mass going in is the change in mass going out. That'll become important in our energy balance equation because those will just cancel. So since it's steady state, M in equals M out. Okay? So now that we have this all set up, we want to force an energy balance on the system. As you remember our energy balance equation from before, it had kinetic energy, potential energy, enthalpy, change in mass, change in time. All of those are going to end up canceling because it is adiabatic and steady state, so nothing is changing over time. So we have no change in kinetic, no change in potential, and we also have no change in mass because it is steady state. So, and we don't have to do our dt. There's no change over time. So now this makes everything really nice because on the left side of our energy balance equation, it's just going to end up being 0 because all of these things are 0. So we're left with 0 equals, we do still have our enthalpy. So we have our enthalpy in minus our enthalpy out. So then we can just set them equal to each other. Enthalpy in equals the enthalpy out. So now what we want to do is we need to incorporate our heat capacity, or for the change in temperature. So in order to do that, we need to note that the flame is significantly hotter. So we can't multiply it by like a constant heat capacity like we've done in the past. We need to integrate it with respect to this temperature. Because we have such a hotter temperature, we can't just do the CP. So now we're going to do our heat of formation equation. So we're going to put that, I'll put that over here, HSF, heat of formation. So that's the variable that we're going to use for that. Sorry, I'm actually. Heat of formation, this is just our final flame temperature. We don't know what it is. And what we're going to do is we're going to set that equal to the original temperature, the heat of formation at 298 Kelvin, but then we need to add in the integrated temperature with respect to the integrated heat capacity with respect to time. So we have integrated 298 TCP dt, just like that. Okay, so this is our heat of formation equation. The next thing that we need to do is we need to go over and use ChemCAD equation 107, and that it's kind of a complicated equation, so I'm just going to copy it from, you can just Google ChemCAD and copy it from there. So I have it written down. So it is y So this is our ChemCAD equation 107. You can just Google this. Obviously, it's pretty complicated. A, B, C, D, and E, we are all going to get from our file that we'll import in Colab. And then we're actually going to use Wolfram Alpha to integrate this because it is so complicated. So we'll just have the computer do that. I will show that in the next video. But before we go to the computer, what we need to do is we need to balance our equations of the fuel using stoichiometry. So I'm going to erase this over here. And we're going to do that so that we know what our coefficients are for our equations for each of our compounds are when we go to solve for the final temperature. We need to know how much carbon, hydrogen, oxygen, and nitrogen we have. So first let me write down compounds. We have methane, which is CH4. We have ethane, which is C2H6. And we have N-propane, which is C3H8. So those are what is in our fuel. We also note that we have oxygen and nitrogen from our air, and then the products are going to be carbon dioxide and water after reacting with the oxygen. So we're going to add O2, N2 to all of these. And we're going to get CO2 and water and our nitrogen. So that's what we get for each of our equations, but they aren't balanced yet because we have different amounts of carbon and oxygen and hydrogen on either side, so we need to make sure that they are balanced. And we also need to note the ratio of nitrogen to oxygen in the air when we balance our equations. So we'll write that over here. It's going to be 79 over 21. We'll need to multiply that with the moles of nitrogen that we're using. It's 79% nitrogen and 21% O2. Okay, so now let's start with the first one. We have one carbon in both, which is good. Oxygens are not balanced, so we're going to add two to this side. And then our hydrogens, we are going to end up having two nitrogens. We have our just one here, and then we need to add here. Right? Just double checking that I did that correctly, and then remember for our nitrogen, we need to multiply by 79 over 21. Okay, so that looks good. We have 1, 2, 2, 1, 2, 2. And then we need to do the next equation. So we'll have one here still, but we need another carbon here. And then we need to make sure that we balance our oxygen still. So we have 4, 5, 2 over here. So we're going to end up with 7 over 4 oxygens on this side. And then we have to multiply. Again, our hydrogens are now going to be 3, I think, right? And then for our nitrogens, we still have, we're going to have 7 over 4 for our nitrogens too. Okay, sorry it's getting a little messy, but we have 1, 7 over 4, 2, 3, 7 over 4. Okay, just one more equation. 1 here, balance our carbons first, 3 carbons over here, and then we need to balance our oxygens. We're going to have 4 over 5 over here. Same for the nitrogens. We're just going to have 5 to make 10, 79 over 21, 5, 79 over 21. And then for our water, we need to have 4 to balance with the 8 over here. Okay, so we have 1, 4/5, 5, 3, 4, 5. All right, so now all of our equations are balanced, even though it looks a little messy. It'll make more sense. We go to CoLab. We're going to start with, I'll just make a couple last minute notes here. Our nitrogen, since it's in the air, the initial temp is 298 Kelvin. So if we were using pure oxygen, our flame would be much hotter because we have to, since we're using air, we also have to raise the nitrogen temp. So we need to note that the temperature of our flame will be lower. So because of this, temp, flame, lower. Okay? Because we're using air instead of oxygen. Alright, so I think that's all we need the board for. I think we explained the concepts pretty well, and now we're going to go to CoLab, put our equations in, and use ChemCat equation 107 after integrating it in Wolfram Alpha to determine the final temperature. Okay, so in this video we are going to finish up our problem for the adiabatic flame temperature, and we're going to start with, this is our ChemCat equation 107 that we copied on the board, and this is what we are going to integrate for the heat specific the temperature of the flame component in our adiabatic flame temperature problem. And so what we're going to do is we're going to take this formula here and we're going to go over to our Wolfram Alpha to integrate it. So here we are, And first I'm just going to put in what we have for the first part of the integral. So we're going to type in integral, and it was integral of c over t divided by hyperbolic sine of c divided by t squared I think I'm missing. Okay, I think that's enough parentheses. And over time. See what that gives us. Okay, sweet. So this is the integral of that. This is the first part, and this is what's going to be multiplied by our b. As you can see over here, we have our b terms times this. The a we don't have to put in because it doesn't have this complex. We're just going to do this part times d. And then those are what we're going to use multiplied by their coefficient in our collab. So this is that here. All right, we're going to next, to do the e, I'm just going to change this to an e, this to a hyperbolic cosine, this to an e, and then everything else remains the same, but this time it's multiplied by d instead. And Wolfram Alpha changes these to little e's, but it's still the constant e. But so now this is what we have. We have e times hyperbolic tangent v over t plus constant, but the constant's not going to be important for us. So now that we have these, we can use them in our collab. This is multiplied by d to integrate in order to solve our adiabatic flame temperature to find the final temperature. And so over here now we're going to use collab, and I've just loaded in the data from our GitHub site as the tools that we're going to use. I'm going to cut this out. I'm going to cut that out. Okay, I'm going to drink some. Okay, so this is what we start with. This I just imported from our GitHub site, and we also have our numpy as np, and we're going to use our root solver. And then these are our tools, so we can see these as a file, and this is what gives us our different coefficients and parameters for that. Oh, I have to load them in first. So now it should be over here, CHE tools. We can see all of our data in here. So, we're going to have our methane properties, which then pops up over here. Didn't mean to do that. I don't know if I can see this. Anyways, it has all of these in here. Ideal gas, heat of formation, ideal gas here, and it gives us our coefficients here. And we want to note that it's in kilomoles here. So we're going to have to take that into account by multiplying by 1,000 in our dividing by 1,000 in our sensible heat equation. So that's what we're going to do for that. Let's get rid of these. And then the coefficient line, as you saw, is for the ideal gas heat capacity, and it's just, for the A, B, C, and D of the ChemCat equation 107 that we will be using. We can just grab those from the file itself because it gives us the coefficients, which is helpful. So now what we want to do is we want to import our properties for the different compounds that are in our fuel. So we're going to do P equals CAG props, and we're going to do, we have methane, ethane, and propane, oxygen, nitrogen, carbon dioxide, and lastly, water. Load that in there, make sure you've typed everything correctly. Okay, sweet. Next step, we want to establish all of the moles in our fuel, which is what we did, the stoichiometry balance of equations on the board. So we're going to start with the coefficients for our carbon and our hydrogen. So what I'm going to type in here, we're going to call it the fuel carbon hydrogen, and that is going to be equal to, we're just going to create our array here, sorry, parenthesis, and we have 1, it was 1 and 4, 2 and 6, and then 3 and 8. Oops. Load that in there. What did I do wrong? Oh. Any parentheses in all of these? Or commas in all of these? Okay, there we go. Sweet. Now the next step is we want to create a variable for our actual moles of fuel being put in. So I'm just going to call that N fuel, and we want to set that equal to the array, and we're going to say there's 10 moles, 1.5, and 1 for our carbon, hydrogen, and oxygen. Okay, load that up. Why do I keep typing in things wrong? Silly me. Need my brackets. Okay. The next step now is we need to find a dot product for the two arrays that we just created. So we're going to do moles of carbon, moles of hydrogen, and we want to set that equal to the matrix multiplication of the fuel, the number of moles in the fuel and the moles of carbon and hydrogen. So we're going to do N fuel, the at symbol, okay, at N underscore C, or sorry, it was fuel underscore CH. Sweet. Oh my gosh. I'm really struggling with what's about fuel. Okay, better. Alright, so that's good. Now what we need to do is we need to get the different mole values for the other compounds. So we're just going to define a bunch of variables here. We're having moles. We had carbon dioxide, and that is going to be equal to the moles of carbon. We had water, and that is equal to the moles of hydrogen divided by 2. We had nitrogen, and that is equal to our ratio, the 79/21, and that is also multiplied by the moles of O2, which I'll put up here. We had oxygen, and that equals the moles of carbon plus moles of water divided by 2. In parentheses. Load that up in there, make sure I typed everything in correctly. Sweet. Okay, so now the next step is we need to merge the matrices. We want everything coming into the system to be in one variable. We're just going to call that the number of feed moles. And so we're going to be using numpy concatenate to do that. And this is where we're going to use our moles of fuel and then the array of the oxygen, nitrogen, carbon dioxide, and water. So we'll have N fuel here. And then we'll have our array, and we will put in our moles of oxygen, moles of nitrogen, and then for everything coming in, we have 0 moles of carbon dioxide and 0 moles of water. Okay, load that in there. Sweet. Next up, we want to do the same thing for the products. So I'm going to call this N products, and we're going to set that equal to NP concatenate, and that is going to be equal to, now the fuel is going to be 0, but we want the size of the array to be the same as the other one, so we're going to do NP dot zeros for the fuel, but we want it to be like N fuel. Okay. And then we will have our array again, and this time we will have 0 of our oxygen, we will still have moles of nitrogen, and then we will have moles of CO2 and moles of water. Okay. Oh, I keep doing everything wrong. Because I can't spell. Okay, now that we have that in there, we are definitely making progress, but this is now where we're going to use the ChemCAD equation from that we integrated earlier for the heat of formation of the final temperature. So we want to create a function that returns the integrated function of our heat capacity. So what we're going to do is define our variable here, and this is going to take values from our tool palette that we imported above. Okay, so we're going to define a function called delta heat formation of an ideal gas at our temperature, and we want it to return our variable, or sorry, our ChemCAD equation with the specific properties from our toolbox. So let me put in here, it's going to be P dot specific heat of ideal gas, and we want coefficient A multiplied by the temperature. Okay. Adding coefficient B. Multiply that by C divided by, it was the hyperbolic tangent times coefficient C divided by T minus coefficient T times E times hyperbolic tangent of P dot, why do I keep doing that? There's not supposed to be. Coefficient C, or sorry, E divided by the temperature, and then remember we need to divide by 1,000 because the data in the files is in kilomoles. Okay, well, it loaded in. Hopefully I typed in all of the parentheses correctly. Now, the next step is we need to get our heated formation at our final temperature. And it's at, so in order to do that, we do the heat, it's essentially the heat of formation at our starting temperature plus the change in heat of formation. So we're going to define another function, heat formation, ideal gas. We need the number of moles and the temperature. We want it to return, and we're going to do the dot product of the functions. NP dot dot n comma p dot h g. Okay. Adding the dot product of the moles in the parenthesis here at the temperature minus the heat of formation at 298 Kelvin. Okay, let's see if that worked. Why is my return thing not? Oh, because I didn't spell return right. Oh my gosh. I gotta slow down. There we go. Alright. So now we're almost done. We need another equation for our energy balance. And in order to do that, we're going to put the moles of our feed and the moles of our product into a function. So we're just going to call this energy balance. Okay. Oh, sorry. We're just going to make it B. So now we want to say that our temperature, and we're just going to create our array here. And we want it to return heat of formation of an ideal gas, N feet, the number of moles going in at 298. And we want to subtract the moles, or sorry, yeah, the heat of formation of an ideal gas of the moles of the products at a certain temperature. And I think I have way too many parentheses here. Yeah. There we go. All right. Now, down to our last step, we want to use our root solver from SciPy to figure out what our final temperature is. So we're going to do root, energy balance function, and we want it to be at, we're going to put in our initial temperature as our initial guess of 298. Okay, see if I did it right. Delta HS is not defined. CPIO to C. So close. Where's my other delta HS for to say? Yay! Alright, so here, this X value, 2,717, that is the final temperature, or the temperature of the flame of our adiabatic flame temperature system. So yeah, in Kelvin. Thanks for watching.